Now the first thing we're going to do is the axes family. The axes family has these 4 points that intersect the axis and the unit circle. And what we're going to do for those 4 points is we're going to label all of the degrees, all of the radians, label the coordinates, and label the tangent of all of those angles on this circle. So first of all, in degrees, this first point right here, well, that would be 0 degrees unless you went all the way around. That would be 360 degrees. The dot at the top, does it make sense that this would be a 90-degree angle in standard position? The next angle would be 180. And then down here, 270 degrees. So whatever color you chose for your degrees, write that in for your degrees. And now we'll do the same thing with radians. Well, this is 0 radians, or if you went all the way around, it would be 2 pi. 90 degrees is pi divided by 2. 180 degrees is pi. And 270 degrees is 3 pi over 2. Now this is the unit circle. And so on the unit circle, what would the coordinates of this point be? Because the unit circle has a radius of 1. 1 comma 0. And up here, we would have 0 comma 1, negative 1 comma 0, and 0 comma negative 1. Now this is the first powerful thing that we learned from the unit circle, because now I can ask you some mental math questions, like what's cos of 90 degrees? Cos of 90 degrees, the answer is up there. Is 0. How do we know? Well, it's one of our big ideas. One of our big ideas says any coordinate on the unit circle is always cos comma sine. So if I go to 90 degrees and I go to this coordinate 0 comma 1, whatever the x coordinate is going to be cos of 90 degrees. Sine of 90 degrees is going to be the y coordinate. So sine of 90 degrees is going to equal 1. What about cos of 180 degrees? Negative 1. Sine of 2 pi? 0. Cos of 270 degrees? 0. Sine of pi over 2? 1. Perfect. So we can use those coordinates to do all sorts of quick mental math if we have one of our angles in our axes family. The last thing we're going to label on here is just what tan of each of these angles are, and I'm going to use the radians. Tan of 0 is 0, because remember that tan is sine over cos. So if we did 0 divided by 1, we would get 0. If we did tan of pi over 2, or tan of 90 degrees, well, if we did sine divided by cos, we would do 1 divided by 0, and dividing by 0 is bad, so we're going to say this is undefined. Tan of pi, sine divided by cos, will be 0 again. And same problem that we had up top, we're going to have with 3 pi over 2. Tan of 3 pi over 2 is undefined as well. And this is our axes family. Yes, ready? Next family. 45 degrees. No, not ready. Last family, axes family. So the pi over 4 or 45 degree family. Again, choose your color coding for degrees. The way something is part of a family, so what belongs to the 45 degree family or what belongs to the pi over 4 family, is whenever the angle has the same reference angle. So anything that has a reference angle of 45 degrees will be part of the 45-degree family. So in quadrant 2, what angle would this be in quadrant 2 that would have a reference angle of 45? 135. In quadrant 3, 225. And in quadrant 4, 315. So those are all those angles in degrees. What are those angles in radians? What would the one be in quadrant 2? 3 pi over 4. Now, how did you come up with that? Good. So if you broke this into 45 degrees, does it make sense that this breaks this into 4 equal segments? So he just sort of counted them. This was 1 pi over 4. This would be 2 pi over 4. This would make this 3 pi over 4. So the counting of segments works really well here. How much would the next one be? 4, 5 pi over 4, 6, 7 pi over 4. So that's one way that you could figure out what they are in radians, is look how big the pieces are and count those pieces as you went along. Another thing you could do is sort of the same way that you figured it out in degrees. How did you figure out 135 in degrees? You probably did 180 minus 45, right? If you did that same idea in radians, instead of doing 180 minus, you would do pi minus the reference angle pi over 4. But you're dealing in fractions. So if you're dealing in fractions, you have to have a common denominator. So I would need my pi to be 4 pi over 4. Does that make sense that that's the same as pi? And if I have 4 pi over 4 minus 1 pi over 4, I'm going to be left with 3 pi over 4. Same thing in quadrant 5. If I have 4 pi over 4 and I add 1 pi over 4, I'm going to get 5 pi over 4. And what would I do in quadrant 4? Well, 2 pi is the same as 8 pi over 4. I subtract 1 and I get 7 pi over 4. Now, in order to find our coordinates, what I'm going to get you to do is you sort of have a space between your two circles here, and in this space right here, I would like you to write special triangle for 45 degrees. And what we're going to do is we're going to make a right angle triangle, because that's where we can get sine, cos, and tan. So we make a right angle triangle and we label one of the angles as 45 degrees. What's the other angle going to be? 45 degrees. Now this makes it a special triangle. It's not only a right triangle, it's also, what's it called? An isosceles triangle. What do we know about isosceles triangles? They have 2 equal sides and 2 equal angles. So we know that this side and this side are equal. And that's true no matter how big or how small you make this triangle. So because sine, cos, and tan ratios work for any size of triangle with 45 degrees, we can arbitrarily choose whatever value we like for the 2 sides that are the same. We could choose 1, we could choose 2, we could choose 85, we could choose 6,342.1. But for mental math reasoning, I'm going to just choose 1, because it's going to do a squared plus b squared a lot easier than if I chose large numbers. Now, if those sides are 1, how long is the hypotenuse going to be? Square root of 2. And now that we've labeled this, and we've done this all without a calculator, we can now say, I know what sine of 45 degrees, what cos of 45 degrees, and what tan of 45 degrees by just looking at this triangle. What is sine of 45 degrees? Opposite over hypotenuse. 1 over root 2. And if you were to rationalize the denominator here, and I'm going to do that at this time, multiply both top and bottom by root 2, you would get root 2 over 2. does it make sense that cos of 45 degrees is identical? It's exactly the same. So cos of 45 degrees will also be 1 over root 2 or root 2 over 2. What's tan of 45 degrees? 1 over 1, so we can write just 1. So because we can make that triangle, we can make an isosceles triangle, we can figure out those values just by arbitrarily choosing values for the sides. And if you would have chosen 3 and 3 and gotten square root of 18 for the hypotenuse and used those values and simplified them, you will get the identical answer to all of those. But because we have that special triangle, we can now label this coordinate. Because coordinates on the unit circle are cos comma sine, and we know that cos of 45 degrees is root 2 over 2, and sine of 45 degrees is root 2 over 2. And if we know that any angle with the same reference angle will have the same sine and cos, we can now label our points in quadrant 2, 3, and 4. The only thing that's going to change is some are going to be positive and some are going to be negative. You can either remember which ones are positive and negative according to your cast rule, because cos is negative in quadrant 2 and sine is positive. Or you can just think about coordinates. If I have a point in quadrant 2, does it make sense that my x coordinate is going to be negative and my y coordinate's got to be positive? And that also relates to the cast rule of where things are positive and where things are negative. So in quadrant 3, does it make sense that both of them will be negative? And in quadrant 4, the x coordinate will be positive and the y coordinate will be negative. Finally, we can figure out tan of pi over 4, that's going to be 1. Tan of 3 pi over 4, that's going to be negative 1. Tan of 5 pi over 4 is positive 1 again. And tan of 7 pi over 4 is negative 1. So again, according to the cast rule, tan will be positive in quadrant 1 and quadrant 3, but negative in quadrant 2 and 4. So once you know the values in quadrant 1, you should be able to fill out everything else in quadrants 2, 3, and 4. Because the numbers are going to stay the same for the family, just change whether they're positive or negative. The 30-degree family. We'll start with degrees. So if all the reference angles are 30 degrees, fill in the rest of the degrees. I'll give you a head start. How much of a head start do you want? 5 seconds, 25 minutes? Somewhere in between? How did you do? 150 degrees, 210 degrees, 330 degrees? Radians is pi over 6. Again, I'll give you a head start with the radians. How did you do with the radians? 5 pi over 6, 7 pi over 6, 11 pi over 6. For figuring those out, did anybody use pi minus to figure them out? So if you use pi minus, well now to get a common denominator, pi would be 6 pi over 6. Notice whatever's in quadrant 2 is always going to be 1 less than the denominator. It's going to be 1 less, 5 pi over 6. Whatever's in quadrant 3 is going to be 1 more than the denominator. Because if you did 6 pi over 6 plus 1 pi over 6, you're going to get 7 pi over 6. And whatever's in quadrant 4 is always going to be 1 less than the denominator doubled. Because if you have 2 pi, that's the same as 12 pi over 6, so the bottom doubled. Subtract 1, you're going to get 11 pi over 6. Now, in between your 30-degree and your 60-degree family, in this space right down here, what we're going to do is we're going to draw our special triangle for 30 degrees and 60 degrees. And the reason it's a special triangle for both of them is because if you make a right angle triangle, which tells us our ratios for sine, cos, and tan, and you make this top angle 30 degrees, in order for it to add up to 180, the bottom angle has to be 60 degrees. Now last time, as soon as we drew the triangle and we put all the angles in there, it was another special triangle. It was an isosceles triangle. This time, once we put the angles in here, there is a special name for this kind of triangle. What is a special name for a triangle where all the angles are different and all the sides are different? Scalene. It's sort of a special name for a triangle that's not special. It's kind of sad. But yeah, there's nothing special about this triangle. There's no special properties other than all the angles and all the sides are different. So at this point, that helps us nothing. But if we take this triangle and we duplicate it, so I take the exact same triangle, I duplicate it, I reflect it over and copy it here. So this is still 90, this is still 30, this is still 60. If I put those two not special triangles together and make a big triangle, there is something special about that big triangle. Sorry? It's all equal, right? It makes an equilateral triangle where all the angles are 60. What else do we know about an equilateral triangle? All the sides are the same. So no matter how big or how small this triangle is, all the sides are going to be the same. So again, we can arbitrarily pick a number for one of the sides and put it down. And what I'm going to choose, again, you could choose any number, but I'm going to choose 2 for the side length, because what happens to the bottom then? It splits up nicely to 1 and 1. So all the sides are lengths are 2. If you do a squared plus b squared equals c squared in the blue triangle, you'll find out that that line in the middle is a square root of 3. Once you've labeled this triangle, we can now say, I know what sine of 30 degrees is, cos of 30 degrees, and tan of 30 degrees. I can also figure out sine of 60 degrees, cos of 60 degrees, and tan of 60 degrees. Sine of 30 degrees is opposite over hypotenuse. That's going to be 1 over 2. Cos of 30 degrees, adjacent over hypotenuse, root 3 over 2. And tan of 30 degrees is opposite over adjacent, 1 over root 3. And if we rationalize the denominator by multiplying the top and bottom by the square root of 3, we will get root 3 over 3. Sine of 60 degrees, root 3 over 2. Cos of 60 degrees, adjacent over hypotenuse, is 1/2. And tan of 60 degrees is going to be root 3 over 1, which we'll write just as root 3. So again, if you're able to draw that triangle, make an equilateral triangle and split it in half, you can get all of your special angles and all of your trig ratios for 30 and 60 degrees. Again, we did all of that without our calculator. So now we can go back to our unit circle and say, I can now label these points. cos is my x-coordinate. So what is cos of 30 degrees? Well, for my special triangle, that was root 3 over 2, and sine of 30 degrees was 1/2. And once you figure out quadrant 1, you know all the other quadrants for the 30-degree family are going to be identical. The only thing that's going to change is which values are positive and which ones are negative. And since we know that tan of 30 degrees is root 3 over 3, we know that tan of pi over 6 is root 3 over 3. Tan of 5 pi over 6 is negative root 3 over 3. Tan of 7 pi over 6, again, tan is positive in quadrant 3. And tan of 11 pi over 6 is going to be negative root 3 over 3. We already have our special triangle for pi over 6. I'm going to go down to the bottom circle here. I'm going to label one angle in degrees. So that's 60 degrees. This is our pi over 3 angle. And I'm going to label one coordinate since we were able to figure out that cos of 60 degrees was 1/2 and sine of 60 degrees was root 3 over 2 from our special triangle that we just did. Now, the reason I wanted to point this out is you're going to have to know these coordinates. And notice the coordinate for 60 degrees, 1/2 comma root 3 over 2, is very similar for the coordinate of 30 degrees, which is root 3 over 2 comma 1/2. They're basically the same, just flipped. So when things are basically the same and just flipped, it's very easy to mess them up and make mistakes. So how can we remember which one goes with which? Well, one of the ways that you can remember is just by looking at your unit circle. If you know it's supposed to be either 1/2 comma root 3 over 2 or root 3 over 2 comma 1/2, and you're like, I don't know where the half goes. Does it go first or does it go second? Does it go with my x-coordinate or does it go with my y-coordinate? Well, if we think about our axes here, I have these points. We know that this point is 1 comma 0 because it's a unit circle with a radius of 1. And this point up here is 0 comma 1. If I look at the 60 degrees and I look at the point that I have, and I go down to my x-axis and over to my y-axis, where does it look like a half? On my x or on my y? That red point. Can you see that it looks more like it cut it in half along the x-axis than it does along the y? The y almost looks like it's really close to 1. So if I look at 60 degrees and I say, where does it cut it in half? It looks like it cuts it on the x-coordinate, so my x-coordinate is the half. If I go back to my 30 degrees and I look at that point, where does it look like it's cut in half? Along the y-axis. So that can be something, just an easy visual thing to help you remember, where does the half go? So here I would know with 30 degrees the half has to go with my y-coordinate because it cuts my y-axis perfectly in half. And then the root 3 over 2 would have to go with my x-coordinate. So we've got our first angle in degrees. Label the other 3 in degrees, then label the other 3 in radians. See how you did. 120 degrees, 240 degrees, 300 degrees, pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. And since we have our first coordinate already, we can do the other coordinates. And we can label tan as well. So quadrant 3 should be root 3, and quadrant 4 should be negative root 3. Yeah, and they shouldn't change. So whatever you get in quadrant 1 should make you continue through quadrant 3 and 4. And for whatever reason, I think I started thinking about pi over 4 when I got to quadrant 3 and 4. And so wrote them down wrong.